College. Today's program is designed to explore self organizing map SOM and its implementation with the aim of enhancing and teaching our practices and fostering a supportive academic community. I look forward to a collaborative and insightful session with each of you. This program is designed to help us grow as a community, to exchange knowledge, and to develop new skills that will benefit both educators and students alike. Now it's my pleasure to introduce our session chair, Kamini Kanchan ma'am. We are honored to have her here guide us through today's discussions. Moving on to our second session, I am thrilled to introduce our speaker, Dr. Anjan Kumar Rai sir, who serves as Associate Professor specializing in advanced technological fields at NIT Sikkim with a wealth of experience in multiple critical areas of electrical and computer engineering, including control systems, intelligent systems, robotics, machine learning, artificial intelligence, and electric vehicles. Today, he will be sharing insights on the topic of self organizing map and its implementation, offering us valuable perspectives on this topic. We are honored to have him with us, and I'm sure we all will gain a lot from his expertise. Please join me in welcoming Dr. Anjan Kumar Rai, sir. Over to you, sir.
Thank you, Nandini, for this introduction. Uh, shall we begin?
Yes, sir, you can start.
Okay, I'll share my screen now.
Yes, sir.
So is my screen visible to all?
Yes, sir.
Okay, fine. So I'm very much thankful for this invitation for this faculty development program on the topic next generation technologies in information and communication organized by Bengal College of Engineering and Technology, Durgapur. I am Dr. Ranjan Kumar Ray, an associate professor in the Department of Electrical and Electronics Engineering, NIT Sikkim. And today's my presentation topic is self-organizing map SOM and its implementation. So as mentioned in the introduction, as it is also related to community development and collaboration, so I will briefly introduce NIT Sikkim to you all. The institute is an autonomous institute under Ministry of Education, and it offers BTech in electrical and electronics engineering, electronics and communication engineering, computer science and engineering, mechanical engineering, and civil engineering. MTech in three specializations from the three departments, MSc also in chemistry department, and PhD in all departments. Also, this is a temporary campus operating from Rabangla, Namchi, at an elevation of 2100 meter. So you can see some good pictures that you can also travel from this campus. About my group, I am currently leading the control system and robotics laboratory group. And this group, we have three members already completed their PhD. One is now an assistant professor at IIIT Ranchi. One is working in industry Magnus Tire, and this company is the automation backbone for premier cars like BMW, Audi, Mercedes. Another scholar completed PhD, and he is now postdoc at Max Planck Institute for Software System, Germany. And we have several MTech members. Uh, Mostly they are doing their PhD in NIT Sikkim or other universities around the world. Currently, we are working in different perspective of control system, including soft robotics, intelligent electric vehicle, assistive robotics, and intelligent vehicle control. So going back to our topic today, we are interested in the self-organizing map. Now, as it says that self-organizing map, it means that given a map, the neurons tries to organize themselves to map this given area. Okay, so in this case, the red line, if you see this kind of circular area, this area was given to the set of neurons. And by the way, the self-organizing map is a part of neural network. And these green dots actually refers to such neurons, and they have some connections that we'll explore in our discussion. Now, first, see this video. Is this video visible?
Yes, sir.
Okay. So, what happens here? These green dots, which actually represent one of the neuron, and these neurons are trying to map the given red dotted area. So instead of the circular area, it may be my face. It may be some important area where we want surveillance. So it means that instead of using so many points like red dots, as we also know that between any two points, we have infinite possibilities of points. So instead of using so many of points, we are mapping this space with limited number of neurons. So these neurons actually extract the features of the given workspace. Okay, so I'll again run this video and you'll see that how these neurons interact with each other, collaborate with each other to get this mapping done. Now, why this self-organizing map? Why we are interested in? If I go by this search in the Google Scholar, if you see, if I search this term self-organizing map here, and it results into more than 38 lakhs of references. It means that the self-organizing map is of importance and researchers are interested in this area. Now, even if I go what happens go to this 2024 year, so what happens in 2024, you will see that more than 18,000 references are available for this self-organizing map, and this self-organizing map is being used in different applications. For example, if I go to the previous slide, if you see that I can use this self-organizing map for any type of such clustering work. Okay, and then if I go to this case, I can see this use for structures. I can see that this can be used for multi-objective optimization problem. We can also see that this may be used for medical purposes. Okay, and also I can see that this self-organizing map can be also used for time series work. Okay. Now, if I specifically go for a particular area, so again, if we in the Google Scholar, if we in the Google Scholar, if we search that what is the application of self-organizing map for cancer, so again, you will see that since 2023, we have more than 17,000 references available for this self-organizing map, including some of the areas like breast cancer and cervical abnormality. Okay, and also it can be used for the COVID-19. So it means that if we get some idea about the operation of self-organizing map, we can use this self-organizing map to various applications. So if you are interested in other field for engineering, let's say electrical engineering, you search self-organizing map for electrical engineering, you will see several applications on that. Similarly, I search for this robotics, self-organizing map for robotics, and we see that there are more than 1,80,000 references available. And how these are used, let's say sense of touch. So how we perceive our external environment, one of the aspect is touch, and self-organizing map can be used for interaction of such sensitivity for the robots as well. It can also be used for underwater robot. Also, we can use this thing for robotic manipulator. Robotic manipulator means the way we manipulate our physical environment, like our hand, we can hold a glass of water. So similarly, robotic manipulator can be incorporated with this self-organizing feature map for its modeling and control. Also, autonomous robot. But there are other applications, whatever I got in the single screen, I'm just pointing out. So it means that the topic is important topic. Now, how to understand, how to get hold of this self-organizing map. So today's discussion is mainly on the classroom type of discussion rather than research aspect. So we'll discuss how we can implement self-organizing map step by step. So self-organizing map is motivated by the feature of human brain. The neurons are organized in one or multi-dimensional lattice. And what does it mean? We'll discuss now. The neurons compete among themselves to be activated according to a competitive learning scheme. Competitive learning scheme we'll also discuss, but if you remember the video that I showed, you observe that neurons compete among themselves to get the positional update. So green lines, green dots are moving across the screen. The weight vector associated with the winning neuron is updated. Now, what is winning neuron will also come after a few slides. It's updated and scheme is that it winner takes all. But in this self-organizing map, the update is not only concentrated on the winning neuron which win from the competition, but also we defined a neighborhood of the winning neuron. So in each sample of the neural network, the winner neuron gets updated as well as the neighbor of the winner neuron. Okay, so again I'm repeating, the neighbor of the winning neuron also gets some updates. Now, the structure of the neuron. Now, I mentioned several times neural network, self-organizing map, but how this neural network is structured. First, we'll discuss about the conventional neuron structure. The convention neuron structure is based on macular model. In the macular model, what we have here, let's say this represent one neuron. Pardon me for this drawing. Okay, and these neurons, let's say, has some inputs x1, x2, and like this, I have m number of inputs. Okay, so let's say x1, x2, and m number of input. Now, for this neuron to be activated, each input is associated with one each weights. Let's say this is W1, this is W2, and similarly for this we have WM. So these are weight field associated with each input. It means that if the neuron has two inputs, we'll have weights associated with each neuron in the conventional McLaughlin model. These weighted input are now summed together. This weighted input means here the signal comes like W1, X1. Similarly for this one, and all these signals or these weighted inputs are summed together here. Again, as this is not about the conventional neural network, so we'll not go into details. We'll just mention that this weighted sum is also biased. So B is the bias. So in a neuron, bias may be there, may not be there. If B is bias is not there, in that case, what would be the value of B? B will be 0. Otherwise, B is available. So no bias case. Now, after this whole summation, this goes into a section is known as the activation function. So the argument of this activation function is that weighted summation of the input plus bias. Yes. Am I audible?
Yes, sir, you're audible.
Okay. So after this activation function, the neuron output neuron output is achieved. So if I have a model of this, so up to this point, up to the summation point, we have summation of I is equal to 0 to m number of input. This is summation. This is the weighted summation of the input. But we have also bias, so that is also being added. This is, let's say, the component YB. So here this YB comes. So YB is the weighted summation of the input as well as bias. Now the phi, the output of this neuron is phi of YB. Now this phi is known as the activation function. Phi is the activation function. Now, as per application, you may choose activation function. It may be threshold function, it may be uh, piecewise linear function, or any such mathematical function that you wish to use. And that will actually change the level of this output. But this is the conventional neuron. So I consider only single neuron. This is a single neuron in a conventional neural network. But in the self-organizing map, the internal structure of neuron is little bit different. So now we'll discuss about again the structure of the neuron, each single neuron. So in this case, the neuron, again, the same concept goes that the number of weights associated with each neuron is equal to the number of inputs. So let's say it has two inputs, and it means that inside this it has two associated weights, okay, x1 and x2. But the output, the way this neuron actually behaves, is totally different from our conventional neurons. So based on the structure of this neural network, self-organizing map neural network, we arrange these neurons into lattice, one dimensional or two dimensional or three dimensional or likewise n dimensional lattice. So we'll discuss about such dimension of the structure. One dimensional means, let's say if you have four, let's say six neurons. Let's say we have six neurons. So one, two, three, four, five, and six. So we have six neurons and we give some indexing for these neurons. So each neuron has one index for its position on the network. So this is one dimensional lattice, one dimensional structure of neuron. Now, what would be the input for this? Let's say this is the input. Let's say this is X having X1 to XM, M number of input channels are there. Now, this input is associated with all neurons. All neurons. This input will go to all neurons. So similarly, this neuron, this input will go to all neurons. In the previous case, in the conventional network, if we have multiple multi-layer structure, let's say if we have multi-layer structure, what happens? Let's say in the first layer, I have 3 neurons. I have second layer, I have 2 neurons. In that case, and I have 2 input, let's say X1 and X2. So for the first layer, all neurons will have inputs. Okay, all neurons have 2 inputs. But in the second layer, what happens? The number of input is changed. In the second layer, what happens? In the second layer, the number of input for the neuron, if it is a fully connected, it will be 3. So here 2, here 3. So it means that in the network, if the layer advances, the number of inputs may be different depending on the structure. But in the self-organizing map, all neurons will have same input. Okay. Now what happened if we have 2D network, 2D structure? So if we have 2D structure, in that case, let's say this 6 neuron, if I arrange it into 2D structure, what happens? So it will be 1, 2, 3, 4, 5, 6. Okay. Or it may be like this: 1, 2, 3, 4, 5, 6. So when we have a structure like this, we have also requirement to give its index. So let's say I give it index 1, 1, 1, 2. Similarly, this is 3, 3, 2. So total 6 number of, so 2, 1, 3, 1, like this. So here it will be 1, 1, 1, 2, 1, 3, and similarly 2, 3. Okay, so this is the structure. Now these numbers, this index will be important. This index will be used to understand its neighbor, that we discussed in the earlier slide, that this training will be based on the winner as well as its neighbors. So similarly, 3D we can understand. Let's say 3D means, let's say one lattice, on top of that another lattice of neuron, on top of that another lattice of neuron. So it will create a 3D structure of the neuron. But the common point is that all such neurons will have the same input. So this is the structure point of view. Now, the structure also, in this structure, let's say the neurons also compete with each other. So there are 2 such distances. So one distance is that, let's say in the 1D structure, if I consider 1D structure, 1, 2, 3, 4, let's say. So what is the distance from, if it is becoming the winner? So distance from this winner to this winner is 1. So again, from this 1 to 3, this is distance 1. From winner to this, distance is 2. So from the index, we understand the distance between the winner neuron and its neighbor. In the 2D structure, things will be little bit different. Having the similar concept, but things will be different. Let's say if this becomes winner. So its neighbor, if I consider the neighbor within the neighbor within the distance of 1. In that case, for this neuron, winner will be this winner neuron, the neighbor will be this neuron, this neuron, and this neuron, because all are apart from distance 1. But this distance will be higher based on the index that we recently added to each neuron. Okay, so this will be, so when this neuron becomes the winner, this will get updated, as well as this neuron, and this neuron will get some portion of the update. Okay, now Kohonen actually introduced this novel neighborhood concept where the topology of input data space can be learned through SOM that we observed through this video. In this scheme, the neural lattice can be one or multi-dimensional that we discussed. A neighborhood concept among individual neurons in a lattice is a priori embedded. A priori means we are defining the structure, whether we are interested in one-dimensional structure or in-dimensional structure. It's up to us, depending on the problem and depending on the resources. Resource is important because when you increase the dimension of this network from the structure point of view, the calculation will be higher. The neurons update their weights upon competition. A meaningful coordinate system for different input features over the lattice is developed. So how they these neurons compete with each other, that we'll discuss. So before that, a two-dimensional coordinate lattice is shown here. Let's say in this case we have input x here, and as we discussed, this input is applied to all neurons here. It has around, okay, 48 neurons. It has 48 neurons, and let us consider this neuron is the winner neuron. This neuron is the winner neuron. Now, if we consider a distance of root 2, distance of structural distance. Remember, this is the structural distance. So structural distance, structural distance d less than root equal to root 2, then this neuron, this neuron, this neuron, this neuron, this neuron, all will be its neighbors, like the internal red portion. So all will be its neighbor. But if we consider bigger, so let's say if I consider 2, so in that case our winner and associated neighbor will be this one, 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 this one. Okay, so we will get our neighbors like this. So again, if you increase this distance, more and more neurons will be added as the neighborhood. But remember that this neighborhood is not a fixed structure, because for a given sample, this neuron becomes a winner, but it may happen that for the next sample that neural network receives, for that sample, this neuron becomes the winner. In that case, the neighbor for this winning neuron will be different. In that case, we may get some part of this set of neuron for the proper updates. Okay, so again, as it says, x excites each neuron is associated with weight vector wi, which is also n cross 1 dimensional. Because why n cross 1? Because our input is also having the same dimension. Input may be 1, 2, input may be 6, input may be 500. So depending on your application. But each neuron will have same dimensional weight space. Now a specific neuron wins based on the self-organizing map distance measured between the input space and the wait space. This distance is another distance. This distance is not structural distance. This distance is from the input to its wait space. So how it is calculated, we'll discuss. So on so overall, self-organizing map, this learning algorithm has three steps: competition, cooperation, and weight update. In the first phase, the competition, each neuron compete with each other to become the nearest to the given input sample. So the neuron for which this distance is minimum is described or declared as the winner neuron. So winner neuron is the neuron which is the closest to the given sample, closest to the given input sample. So again, the sample is important because if you change the input sample, next time some other neuron will be the winner, and that is required. Otherwise, only a certain portion of neuron will get trained and others will not be trained properly. So overall, the neural network training will be a failure. What we want that all neurons get sufficient training for the given purpose, for your purpose, for your problem. So that is required. So in that case, we wish that for different input sample, different winner, different neuron become the winner. So in mathematical term, we express this x as our input, as we earlier said that x may have m number of input channel. So m number of weights should also be there in the each neuron. So similarly, as I said, this synaptic weight vector for neuron J is denoted by this. Now, if you see, J means for this jth neuron, but if you see the index 1 to M, it means that this M comes from the input side, the dimension of the input, and J refers to the number of neurons available in your network. So L is the total number of neuron in this network. In this indexing, actually we consider this for presentation 1D structure, but if you have multiple dimensional structure, then the weight may be defined in a different way. Okay, so in that case, instead of J1, so instead of that you may have I and J if it is a 2D structure. Okay, so this is the index if you use 2D structure for the weight space. However, inputs will be same as previously mentioned. The best match of input vector x with the synaptic weight vector wj occurs when this distance, Euclidean distance between the vector x and wj is the minimum. So in so mathematically what it says that ix is the index of to identify the neuron that best matches x is that the minimum of this calculation for for all neurons. So at this moment I have one input sample, but I have l number of neurons, all such l number of distance that we have to calculate for this given input sample. Now, among such, so means for neuron 1, the distance between the weight space and the input space, let it be d1. So similarly, I may have L for L number of neurons, I may have DL, D1, D2 to DL. So what is the minimum distance? Minimum distance is minimum of dj for j is equal to 1 to L. So this is the concept. So I have to calculate this distance from the input space to the wait space and find out the minimum distance for all neurons. Now, example, so far we have discussed about two such distance. One is neuron to input distance, and based on this, actually we find out the winner. And neuron to neuron distance, that is the structure, and we find the neighbor using this distance. Okay, so we have two distance already discussed. One is neuron to input distance, and that the minimum one refers to the winner neuron. And neuron to neuron distance from the structure point of view, like 1D, 2D, 3D, ND, and we get the neighbor. Now, in this neighbor case, let's say uh, if we go for higher, if we go for higher dimensional structure, then for a given distance, more number of neurons will be associated as neighbor of a winner neuron. So this will also sometimes what we observe that gives better accuracy, but thing is that it also increases the calculation. So you have to have a trade-off as per your resources, as per your purpose of your problem. So neuron to input distance, let's say a neuron, for example, if we consider an example here, distance, how distance, let's say this is neuron, it, and we are working on the two-dimensional space. So input is, let's say 2, input is x, and let's say in this case input is, let's say 1 and 2, and in this case weight, associated weight for a neuron, let's say neuron 1, it has weight w1 is equal to let's say 3, and W2 is 4. Let's say randomly I have. So what would be the distance between this? So distance 1 will be, in this case, input to distance. So input 1 minus 3 square plus 2 minus 4 square. So whatever value that will be the distance. Okay. So similarly, if we have another neuron having weight, let's say 1, and W2 is equal to 3, in that case, same input will go to this neuron. And in that case, distance for this, let's say this is neuron 2, so distance will be D2 will be 1 minus 1 square plus 2 minus 3 square. So the value. So among these D1 and D2, among this D1 and D2, whichever is minimum will be the winner neuron. So this is neuron to input distance, and for this, from this we get the winner neuron. And once we have received winner neuron, centering to this winner neuron, we calculate the distance from this winner neuron to other neuron and select the neighbor for the winner neuron. So in the cooperation phase, so once we have achieved the winner neuron selects its neighbor, as we discussed, according to a predefined neighborhood function. So in this case, the original version was the Gaussian neighborhood function was chosen. So this AGI denotes the topological neighborhood centered on the winning neuron I. We'll also see the implementation for that. Also, DJI refers to the lateral distance between the winner neuron I and the excited neuron J. So this is my. So if I plot, if I see that at when distance is 0, means winner itself, age value is the maximum. So its value is 1. So once I move from the winner neuron to other neuron, as the distance increases, the value of the neighborhood function also decreases. Okay, and this neighborhood is also changed according to this formulation. The formula, if you observe closely, observe, this is an exponentially decaying function. It means that over the time, this width of this neighborhood function also decreases. Means, as if I go time more and more time and more sample comes to the network, this will shrink. The neighborhood will shrink. It's like us. Let's say we get more and more mature, then we will see that our close circle becomes narrower. So it also happens here in the network. The same principle is being observed here, that as the neurons getting more and more sample, it means that as the neuron getting more and more mature, the neighborhood become narrower. So again, as I told you that at dij is equal to 0, this is the hij is the maximum point. Okay, and other words, it attains the maximum value at the winning neuron I, for which the distance dij is 0. The amplitude of the topological neighborhood AJI decreases monotonically with increasing lateral distance. It means that as as this distance increases from either side, the age value is decreasing. So it means that from the neighborhood neuron, as the neuron are placed away from the winner neuron, its neighborhood value will be less. So it will get less update for its weights in effect. So we'll discuss during the weight update section. Okay. So with we understand that width is also decreasing as the sample increases. N is the number of training step or sample. So as n increases, this value will also decrease. Again, the neighborhood function is actually defined by this equation, by this Gaussian function, and it is dependent on distance d and also the width of this Gaussian function. Now, again, as we observed in the previous equation, this width is also dependent on the number of samples, and also the time constant tau is used here. So this is used to shrink it, and also the rate at which it will shrink, that will depend on the values of n and tau. We will also show you in implementation for this now, but before that, let us calculate the distance first, because to understand the neighborhood, I need to get hold of this distance as well as this width function. So distance, if it is a one dimensional lattice, so the index, if you remember, index is given as 1 2 3 4 5 6 7 8, like that. So like here example, we have 8 neurons, and let us consider that third neuron becomes the winning neuron. So other distance from this winner neuron for this case would be 1 for neuron 2, and this is 2 for neuron 5. So this for neuron 2, the distance is 1. For neuron 5, the distance is 2, as it is calculated here. So similarly, we can get the structural distance from the winning neuron for this one-dimensional case. If we move on for two-dimensional, the distance is measured like this. Let's say in this case two-dimensional, each neuron has two index. for this you may say that it's a row column arrangement. So if this become the winner neuron, this one become the winner neuron, its index is and 3. And let's say we want to calculate the neighborhood distance for this neuron, this neuron. So its index is 4. So the structural distance will be this. Actually, DJI will be root of that. Okay, so this structural distance is calculated like this, and this structural distance is used in this formulation to find out the neighborhood contribution for the training of each neuron. Now, simulation. So I want to show you a few simulation or implementation for this. Okay, so let us consider this is an implementation. I used an open access platform, Scilab, for this implementation of this neighborhood function. So I give some values of sigma, tau, and let us consider that. Sorry, I'll go for this one. Okay, so this is sigma tau is given, and let us consider that the distance I consider minus 50 to 50. Minus is not required actually to show you the direction from right side and left side only. Okay, the values will remain the same. So in that case, sigma, for each case, sigma is changing using this formulation as mentioned earlier, and the neighborhood function is found out by this distance. This distance is changing as you see in the line number 8. This distance is changing, and also the width is remaining the same. In this case, we are not changing the width. Why it is not changing? Because we are considering the same sample. N is equal to 1 sample, we keep it the same. So see, at same sample, the width remains same, but as the distance changes, we'll see the effect. So we'll run it. We'll run it. Eh, 1 minute. They are having some problem here. Let me see this one. Huh. So here. Okay. So if I smaller it. Okay. So if you see here, the neighborhood function associated with this winner neuron, and you see that at 0 point this has maximum value, but as the distance is changing, the values are changing. But if I change the width, if I change the width, you will see what happens. More and more neurons are actually being added into the neighborhood. So it means that it's up to you how aggressively you want to train your network. So using these values of sigma naught, or also let's say for this case, if I change it to zero point 0.5, let's say 0.5, the time constant, you will see the effect. Again, it goes towards zero very quickly. Okay, so it depends how you wish to perform your training. Am I audible? And these plots are visible?
Yes, sir, it is visible.
Okay. Okay, so what we saw here that we can change the width of this neighborhood function, or we can also change the time constant, and that also changes the number of neurons associated with the winner neuron as neighbor. Now, again, in this case, what happens? We consider the single sample. It means that we consider that one sample of input came to the network and we try to see the effect of the winner and its neighborhood. But what happens if the number of iteration changes? Means more number of samples, input samples come to the network. In that case, what happens that I'm changing to another program here. Here, what is done that this number of inputs are changed. Number of inputs, sorry, is changed. So here in this in this simulation, I consider 10 such sample going to the network. If it goes like this, what happens? We'll see. And by the way, in this case, I consider the same distance for a neuron. Means the winner neuron to the neuron of interest, the distance is, let's say, 5. Okay, but in this case, only thing is changing is that number of samples. If the number of samples changes, what happens to the neighbor of a winner neuron that we wish to observe? Okay, so if you see here in this screen here, so you saw that the sigma value, the width of this neighborhood function initially was 20, and at the 10th sample its value is 3.38 something. Okay, means the width has drastically reduced. Again, for the age value, the neighborhood contribution, initially it was 0.97, and after 10 sample it is 0.33 for the same neuron distant away from the winner neuron of 5 distance away. Okay, so to observe it through uh, simulation and visualization, I extended this to consider few cases. Let's say I have only one sample, and what happens? I have only one sample. Okay, so n is equal to 1, and I consider 50 neurons the right side, 50 neurons left side. So these are the 100 neurons along with the uh, winner neuron for one sample, and what happens to its neighborhood count. See here. So neighborhood, you will see that minus 50 to 50, we saw this kind of Gaussian plot. This is the neighborhood function, and this is distance from the winner neuron. And again, you see that at 0, it has the highest value of 1. And 0 means, 0 distance means it is the winner neuron. As the winner neuron, as the neuron is away from the winner neuron, the age value decreases. Now, what happens if I increase this sample? So let us consider I increase to 2. So if we run it, you will see that again, now the value is decreasing. Value is decreasing for the neighborhood. But again, in that case also, again at 0, the that is the winner neuron gets the highest age component. Now to understand it better, I increased, let's say, 8 samples, and you'll see that how gradually it diminishes. So it also means that as the neuron gets more and more samples, that is, as the neuron gets more and more mature, its neighborhood shrinks. So this is the concept of the neighborhood introduced by Kohonen for this self-organizing map. Now again, coming back to our presentation, so we have already covered two part, competition and cooperation, and weight update. Now weight update. So weight update, weights associated with the winner neuron and its neighbor are updated as per a neighborhood index that we discussed right now. Also, we introduced a learning rate. Learning rate. Okay, so this is the learning rate. This is the learning rate, and we also consider this learning rate to as per this exponentially decaying function. But you are not restricted to use this function. As I said, this is a kind of classroom interaction, so that's why we, but if you are doing some research work and your work this requires some other activation and some other learning rate, you can choose. And this weight, each weight is updated based on this learning rate, this neighborhood function, and also the distance from the input to its weight. Okay, component wise distance. And the final update is that the update of neuron, jth neuron at n plus 1th sample will be the previous weight plus this learning rate, this weight, neighborhood function, and the distance from the input to its respective weight. So this is the total uh, learning scheme for the self-organizing map. Now use cases. So first we observe this self-organizing map operation during initial phase with circular workspace. Here the workspace is changed to a rectangular and space, and these neurons are actually the green one, these neurons are actually randomly placed, and also these are having two-dimensional structure. Now see what happens. So it means that the neurons also compete with each other, coordinate with each other as a neighbor, and also updates updates uh, update their weights, map this given area. As I mentioned earlier, this area may not be always circular or this rectangular. It may be 3D shaped also. So depending on your problem, you may choose your input space and try to train your neurons as per the given space. So again, if I give you the 3D structure, here initially the neurons, the blue ones, the neurons are actually initialized here, and it was given a space like this space to cover with having a three-dimensional structure. This space was given as its input space, and when neurons are trained, these neurons goes up and then try to cover this. You see some green spots there. These are the neurons that uh, goes to this given workspace. So if I try to implement such thing, I'll show you. I have also very little time probably, so I'll just show you the representation that is actually the full representation and implementation of the self-organizing map. And we consider 4,000 sample in a three-dimensional space, having considered 100 number of, I mentioned here, you see UAV. It means that you can use this type of program for surveillance work or area coverage using unmanned aerial vehicle as well as. Okay, so if I run it, you will see this figure. So it is still running. So let me, you see these neurons are initially here, and this upper blue space were required to be covered by these neurons, or here in this case, let's say drones or UAV. And you saw that these UVs are placed, these green dots you can observe probably, the green dots are there, which are the finally trained version of this UAVs. I'm not sure whether green dots are visible or not, but is it visible?
Yes, sir. The blue dots are visible.
And green, there's
Green.
some,
Yes.
you see here green.
Yes, the green dots are also visible.
Yes, so green dots are basically the neurons that actually came from this initial space to this desired workspace. Okay, so I'll conclude here. And if you wish to wo- collaborate with us, here is my email ID. So we can work on different aspects of automation. We work on control system applications in different fields, optimization, AIML also. So thank you very much for giving me this opportunity to discuss and to present this work.
Thank you so much, sir. With this, we have some doubts from our viewers on YouTube. So, for you, with your permission, I will be starting the doubts. The
Yes.
first question is, sir, what is the point of finding best matching unit in a self-organizing map?
Okay, so let's say, as I mentioned, that each sample, and for each sample, the neurons compete with each other to become the winner. And also, if it becomes a winner, the associated neighbor will also be friend. So that's why we want that at different sample, different winning neuron should come out, and it will be also trained along with its neighbor. So the training process will be somehow distributed over the whole network. Even if you see this picture here, uh, if neurons are not trained properly, then you will observe that few of the neurons will go to this upper space, and most of these neurons will remain at its initial workspace. So overall, the training of the network will be a failure.
Thank you, sir. So, the next question is, what is the difference between clustering method and SOM?
So SOM is also a clustering.
Okay. So,
So here, this cluster is also given as an input. So input this actually covers this, as I let me show you. So here also, this space is given, and these neurons are actually trying to cover this space. So this is actually making a cluster of these neurons covering this input space. So this is
okay.
also a method of clustering.
So the next question is, what is the significance of the best matching unit in SOM?
Yes, as I told you, this is base matching unit, means this is will be the winner one, and it has the privilege of highest training, because if you go by this training rule here, if I go again to this equation, so weight update is mostly dependent on this neighborhood side, and this age is maximum for the winner neuron,
Okay, sir.
as we saw in the Gaussian distribution of this neighborhood function. So winner will receive the highest update, and gradually, as the neurons are away from the winner neuron, the less update will happen.
Okay, sir. So the next question is, how how do neighborhood functions influence the training of SOM?
Yes. So neighborhood function, if you remember, so this neighborhood function, if the screen visible with slide number 22.
Yes, sir.
Okay, so the equation, you see this is a function of distance. This distance is the structural distance of the neurons, and this is also the width. So as the distance changes, even it is visible from this figure, as the distance increases from the winner neuron, the contribution of the age is also becoming less. And also, if you remember the contribution of the sample, we saw that as the number of sample increases, this width is also getting narrower and narrower. Narrower and narrower, it means that for the same distance value, initially the value of h will be this, but after certain time the value will be very less compared to the earlier one. So it means that neighborhood concept is very important for this training purpose because it also influences the value of age to a large extent.
Okay. Sir, with this, we have one more question that what happens if the neighborhood ratio in SOM sets to 0?
No, in that case, yeah, it is becoming like that actually. If I run the plot again, okay, so let me see this one. Let's say instead of 8, I use, let's say, 20. So 20 sample I use. You will see that gradually what happens, my neighborhood is shrinking, and actually concentrated towards 0. It means that after a certain time, the training will be concentrated on the winner neuron itself. But it happens not in a single shot, rather gradually.
Okay, sir. Sir, and there is one last question that what are the common applications of SOMs in real world scenarios?
Okay, let's say I mentioned about the manipulator. Let's say our hand, we do not have a defined equation in mind, but we'll still do all sorts of manipulation work without knowing the hand kinematics and dynamics, having no idea of the equation. So self-organizing map can also be utilized for this case where I can map the joint angles of my hand, instead of my hand, I will say the robot's hand and the workspace. So if I can map the joint angle and of robots, of the robot hand or robot manipulator with the workspace, then if I give a point on the workspace, I know what would be the joint angle for each such joint of the robot hand. So if I can move the robot hand with those angles, I will be sure that it will reach to that point on the workspace like we do. But in that case, we don't have any equation for this mapping. So that also I mentioned that we can use surveillance purpose for unmanned aerial vehicle. If we want to survey an area, this application, let's say this is an area where you wish to place some drones at a strategic location or autonomously. So in that case, your drones may be located in your let's say command center, but you send these drones to a strategic location, and the strategic location you are not manually setting, rather this positions comes from the neural network training under this self-organized map.
Thank you,
Okay,
sir. Thank you for your valuable time.
okay,
And
thank you, ma'am.
also thank you for sharing such a valuable and informative knowledge with us. We are ending this session with a positive note that the BCET College, will have some more sessions with you and will have some more collaborations for the research also, sir. Thank you so
Thank you
much
so
for
much, ma'am.
sharing
We're
your
looking
email
forward to
ID
that.
and thank you for offering us the research work, sir.
Thank you, ma'am. Thank you. I'm signing off.
Yes, yes, sir. You may.
Okay.
Thank you, sir.